So we're happy to introduce Andrew Lenforsky, who has actually pre-recorded his talk. So we're here to say hi, and he'll be answering questions throughout the talk in the chat. And yeah, and then we'll come back together after his talk to answer any of the important questions from the chat. So without any further ado, here is Rusty USB Gadgets Make Barking BeagleBones.
Off and running. Thanks, James.
Oh, Flocky, we don't have any audio right now.
Audio.
All right. Well, we're sorting out some of that audio. We'll be back shortly as soon as we sort out the audio.
Uh-oh. Greetings, fellow oxidizers, and welcome to this session of Oxidize Global 2020. Rusty USB Gadgets Make Barking BeagleBones. I'm your host, Andrew Lenforsky, saying hello. Greetings, y'all. I'm actually coming at you from Austin, Texas right now, so I actually get to use that particular contraction. And since this is my first time actually doing videos, I guess I need to do this. Yo, YouTube, make sure you actually smack that button, ring that bell, and hit those likes. And now, presumably, I actually have to give you YouTube face. Okay, and now that we've got that out of the way, we can actually get back to what's going on. What are we actually going to be doing in this session? Well, we're going to convert a BeagleBone, which is the thing you see here on the left, and we're going to convert it into a mouse. This seems like an awful waste of a lot of hardware, and it actually is. But it turns out that this is actually the first step whenever you want to create any form of USB HID device inside Linux and actually make it work. So who am I? I'm currently the VP of Engineering for Third Wave. We're an IoT company, and we specialize in secured FDA-cleared systems. I'm an expatriate full custom VLSI designer, now hides behind software. So when everybody says full stack, I laugh a little bit because my full stack goes down to a few orders of magnitude smaller than most people's. I first wrote C on an OS 9 system, so you can tell this beard's getting very gray. At some point along the line, I actually became the oldest dude in the room instead of the youngest dude in the room, and somehow I didn't seem to pass in between the two states. It just went from one to the other. I guess it's a quantum thing. So I've written some other code, which you can go dig through, but we've got a lot of stuff to cover, so I don't want to waste a lot of time on that. Why am I doing this? Or more particularly, why would you want to do this? You want to make a USB device. Generally, this is meant to interconnect some piece of hardware interface to Windows, and quite often building the USB device code in Linux is way easier than dealing with it in a microcontroller development kit. In particular, in this instance, we're actually building a HID mouse, which is one of the simplest things. So there's a little bit more boilerplate than actually you would normally give. But in this relative to the functional code, but this actually generally holds. The biggest problem when doing this generally is documentation. The issue is that a lot of this stuff is scattered around in bits and pieces, not all of it presented into a coherent whole, and not all of it presented into functions where you can actually work. In this instance, I actually have committed the code to a code repository. I put that on the entry slide, and you all can dig that down. So if you want to follow along at home, you can. I suspect it's a bit early for most of the folks in Europe right now, so they probably will be following along later. But if you want to download it, it's there. In this instance, we have a HID mouse driver, which is what I'm going to do in this talk. And I've actually got a HID generic driver, which does ecosystems. And that's not actually going to be covered in this talk because I've only got 20 minutes. So Let me give a baseline here. What's actually a BeagleBone? When I actually tried explaining the concept of this talk to some people, that was actually the first question that they gave me. In particular, a BeagleBone is a ARM-based microcomputer with actual Linux OS on it. It's an ARM, it's 1 gigahertz, it's got 512 meg of RAM, and it does micro SD storage. A BeagleBone Black, which is the thing you saw here on the left, actually is about $50. And the thing on the right is called a Pocket Beagle. It's actually about $25. Both of these are widely available, and both of them have, roughly speaking, the same interfaces. They all have standard computer interfaces. The BeagleBone Black is a little more, it's already pinned out. So as you can see, it's got Ethernet, USB host, HDMI, micro SD. These things also have standard embedded interfaces, USB devices, GPIOs, SPI, I2C, UARTs, CANs, LCDs, and a bunch of other useful stuff. They also have what are called PRUs. That's probably a talk for another time. These are a pair of 200 megahertz RISC cores that just have some really useful weirdness to them. One of them in particular is that you can actually load 32 registers between the two pairs, between the actual RISC microcontrollers in one clock cycle. That works really, really well when you want to actually move something from hard real time into soft real time, and then actually even the softer when you're actually moving it down to Linux. But that's a talk for another day. We don't have time to go into that. Second baseline, what's actually a USB HID device? A USB HID device is nominally supposed to be a human interface device. So these are things like keyboards, mice, game controllers, foot pedals, stuff like that. These kind of devices want to be guaranteed to be pulled regularly. So in the case of keyboards, they want to make sure that you pull something like once every millisecond or once every couple of milliseconds. They generally return small amounts of data. In this particular case, 64 bytes or less. That's actually a limitation of full speed. If you actually have a high-speed device, they can return a lot more data, but we're not going to cover that. And these happen to comply with what's called the device class definition for the human interface device. These particular mechanisms are actually defined by the USB consortium and actually are something that we actually normally comply with. USB HID devices, these are standard HID devices, your everyday ordinary wired keyboard, wired mouse. Foot pedals are something people often forget about. They're actually a HID device. We'll talk about that a little bit later as well. They present some interesting problems. And probably even your USB keys, the things you use for authentication, are a standard human interface device generally. There's no particular reason they're not exchanging huge amounts of information, so they probably sit there, although some of them may be slightly different. These also are USB HID devices. Although some people will recognize these, especially embedded. These are debug probes. So, and this over here is actually an RF attenuator, and this is a USB to IEEE 488 GPIB converter system. The interesting question here is, these are also human interface devices. So you're probably scratching your head a little bit as to why these would be considered human interface devices. Well, you're about to scratch your head more. These are also human interface devices. In fact, there's actually 96 of these. This is actually a fixture for accelerated testing that I worked on in the past. These are actually sold to people and actually are in fabrication lines and things like that. Every one of these devices is actually a human interface device. In particular, these are 96, and this entire system actually has a lot and is all driven off of one. In fact, it's probably one of the larger USB HID systems you've seen. It actually has 96 USB devices. That presents some interesting problems in and unto itself. So the interesting question you're probably asking now is, what in the world are you talking about with human interface device, and what does that have to do with what's going on? In this particular instance, it's a particular, someone called it abuse of the HID specification, but quite often there were actually very good engineering reasons for this. Back in the old days, we tended to create HID devices for two primary reasons. The primary reason was that for many, many, many years, the only way to actually attach a USB device to Windows without actually having to write or install a driver was actually to call it a human interface device. If you could get away with that, you could actually attach a thing directly to Windows, and then you could start attaching it via various Windows calls. In particular, a lot of things were written in Visual Basic 6, which is probably too old for some of you, maybe even a lot of you who are watching this talk, but because that's circa 1996. But that was the way it was back then. A secondary reason was that USB endpoints were minimized when you were using HID devices. So you really only needed you only needed 2 endpoints when you were doing this, besides normally your endpoint 0, and that was a minimum. Back when RAM usage was a big deal, that really mattered. So some of these USB devices were built USB full speed. I don't think I've ever seen anything below that. But these were running on devices that had maybe up to a couple kilobytes of RAM and maybe 32K of flash. This obviously isn't a particular consideration now, but that was why a lot of these were chosen, and especially when they rolled forward. So one of the questions you need to ask is, why would you want to implement a new HID device? One of the things is you might actually need an actual HID human interface device. In one particular instance that I bumped into, I needed multiple foot pedals. These foot pedals that you saw earlier don't tend to cooperate very nicely whenever they're plugged into multiple systems. So if you can actually concentrate them into a USB hub and then use a HID device to actually pull all of the things together, that's fine. In addition, quite often, if you want to use the foot pedal for something like a control key or a modifier key, not all operating systems will actually allow you to do that directly, where they can combine a modifier on one USB device and a key pressed on another device like a keyboard. A second reason why you might want to implement a human interface device is you may actually have new hardware that you want to get your software development team up and running immediately. A lot of stuff can be faked on these particular mechanisms. And, to be perfectly honest, you can actually implement a lot of stuff in a Linux computer. You can also upgrade USB full speed to high speed. Most microcontrollers are still running at full speed. There are a few that have made the jump to high speed. They tend to be more expensive, whereas most of the Linux computers all run at least at high speed. In addition, USB-C is just not on the map for microcontrollers, whereas a lot of the Unix Linux systems are actually running USB-C. They're a little bit more expensive, but they actually have USB-C today, including all the bandwidth that goes along with that. You may also want to be adding features to a domain-specific device that uses HID. In my instance, that was the actual reason why I wanted to do this. In particular, I had some issues with debug probes. We were using them in very high volume mechanisms, as well as we wanted to do certain things like add encryption keys and install as well as check the device at the same time. You may also have a legacy thing. One of the things that you saw earlier was the fact that we actually had a IEEE 488 interface. That's called GPIB. That standard goes way back to the 70s, but still a lot of lab equipment uses it, especially things like spectrum analyzers and vector network analyzers, which are fairly expensive pieces of RF equipment. So the real question here is, how do we create a HID on Linux? In this particular instance, the first thing we need to do is we need to take over the gadget system, because if we don't do that, what happens? The BeagleBones actually make use of the gadget system themselves. So when you plug them directly into your USB device, your USB hub, or your USB computer, they automatically come up as a Ethernet device. In fact, they come up as 2 different Ethernet devices, one for Linux, one for Windows. We can talk about that. That's something for much later. And so we need to take care of that. The next thing you do is you need to actually set up the USB gadget on Linux using the config-fs. If you use the config-fs, you actually have to do some fairly magical things. They're straightforward. Not all of them are duplicated. Not all of them are documented, sorry. And several of them are generally, when they are documented, they're in pieces. So this actually gives you I will give you a full script. It's in the code base where you get all of the pieces you need in order to actually bring that descriptor up and running. Finally, you need to attach to the created character device, and then you read and write the USB reports. In this particular instance, we're going to be using Rust, but you don't actually have to be using Rust. That's not a requirement here. Linux takes over some of the heavy lifting, so it actually avoids having to be required to do it in fast real time. So you could even use C and Python. We're going to use Rust. We have to use EPOL. That's kind of annoying, but we're going to do that because it actually works, and you need to see what's going on. A lot of the Rust libraries wrap that, and they swallow it, and they do weird things. So we need to use it directly, which means we're going to call libc. And after that, it's alive. So let's see how we're going to do this. Let's start looking at what's going on here. So the first thing I said is that we need to grab a hold of the USB device. And we need to grab all of the gadget system in order to actually do what we need to do here. In this instance, this system actually what we're doing is we're actually taking down what's called the composite system. And this is actually specific to the BeagleBone Black, or it's actually specific to the BeagleBone family is probably a better description of it. In this particular instance, a lot of what we're doing here certainly also can be used with a Raspberry Pi. There's nothing stopping you from doing this. The gadget subsystem is the same. And now let's reboot that BeagleBone while we're talking about that. So there's actually nothing which is stopping you from using this on a Raspberry Pi. And it doesn't matter what Linux system you're on, the gadget system works the same way. So I've already cloned my repository in here. So we've got a barking BeagleBone system, and we're going to go down into the hid generic, the hid mouse, because that's what we're actually doing in this particular instance. And we're going to take a quick look at the actual script that does this in order so that we can see what's going on. In this particular instance, the script starts off with, let me go to the top, where we actually tell the Linux kernel that we actually need to use a libcomposite system. And this actually pulls in the requisite modules that go along with that. We actually then go into the config.fs space of the kernel, which is where we're going to actually have to put our USB gadget. We make our own directory in here to actually hold what's going on, and then we cd into it. There's no point in me being redundant about that. We're going to define some variables. These variables are then going to get picked up by the gadget driver in order to actually fill out USB reports when it actually needs it. This is a particularly interesting problem in that what will happen is Linux will intercept most of the calls, and so the only thing we have to do the only thing we have to deal with are the actual reports. All the things like NACs, stalls, unplug events, replug events will all be handled by Linux. This tells us we're using the USB 2.0 specification or later. Vendor is normally issued by, this is a code that will be issued by the USB consortium if you actually need that. This is a product ID if we actually need that as to where we're going with that. We define that as well as the version. In this instance, again, some other strings. So when we actually, these are generally by convention, they exist. And we can actually create a configuration descriptor. The most important piece here is actually how much power we request. If you request too much power, you can't request more than 500 milliamps. But if you request too much power, it may refuse to actually connect you when it does it. After here, we actually start doing some things. These actually call into the Linux driver. So be careful as you start making these, as you start creating directories and echoing commands, you actually start winding up causing things to go on inside the Linux kernel itself. The module's actually executing at that point. This calls alloc instance, which starts allocating memory. This sets up the protocol. In this particular instance, protocol is defined by the USB consortium. This is a mouse. Subclass, this is normally 0, but in this instance, a mouse. Mice can be used during boot, so they have a boot interface. And in this instance, we're claiming that our maximum report length is 8 bytes. This enables us to use very old full speed or even slow speed USBs because this minimizes the size. This magic block of hexadecimal numbers is, of course, gobbledygook. You really can't understand it. In this particular instance, it's actually copied directly from the USB consortium because it's a mouse. They often provide you with these kinds of helpful things. This actually is a full description of what your USB descriptor should look like, of what your report looks like. You're going to be sending this, and this, your host, the computer, will actually request this from you, and this is a description of, hey, this is what I'm going to send you when you actually ask me to send you something. You can unpack it. There's actually a very nice online tool for unpacking it. I'm not going to go into a lot of redundancy about that. You can look at it yourself. In particular, the things to note about this is the fact that we have a report count of 3 and a report size of 1. That's bits. So these are the buttons. So we're sending 3 bits for buttons. And then we have a report count of 1 of size. So those are 5 extra bits. That's packing because now we actually have a full byte in the report. In a sense, we have usage for X and Y of the mouse. In this instance, it's assigned 8-bit number, so we're actually telling it that it's actually -127 to 127. The report size is 8 bits, and we've got 2 of them. So we've got an X and we've got a Y, and that closes it. At this point, you've got the configuration descriptor is in place. When you actually link this up, it actually calls allocate in the kernel module, which starts bringing the USB subsystem online. Actually linking to the UDC actually calls bind, and at that point, dev hid G0 now exists. You can actually plug the cable into your USB host, and it will actually recognize it as a mouse. We're not doing anything yet because we haven't actually attached anything to drive and eat reports, but that's coming. At this point, you can actually look at it. It's being pulled, and it's sending back what are called MACs. So in this instance, I'm going to actually run this script, and that's actually going to set us up. It would actually help if I, instead of trying to do that on my mechanism here, I actually did that on the device itself. Okay, BeagleBone. This is on the BeagleBone. And hit mouse. And that's actually now ready to go. So at this point, we switch over to the Rust part of the world. And we're now sitting inside Visual Studio Code, which is actually running stuff on our mechanisms here. So one of the first things to do is that we go down in here. Everything is in a main RS. I'll actually get down in here. So we can actually see that there is actually a hid mouse Rust. And if we actually run this directly, our cursor actually starts jumping back and forth. So we'll get back to that. So what's going on inside the Rust? We actually steal a macro call directly from Tokyo in this instance. This is very useful because this allows us to go down into libc, and it actually wraps the result of libc, which is a little screwball because of errors. It allows us to wrap this and return directly into the Rust results for error, which is very useful rather than having to write this boilerplate every single time we need to hit libc. We go down into main. This is some basic stuff for logging so that we can actually enable that. Standard open idioms where we actually have to chain back together in order to make everything work. Still not a big fan of this. Really would prefer that Rust finally get keyword arguments to make life better. We can, in this particular instance, we're switching that device into what's called non-blocking mode. So when we read or write to it, if something happens where it can't complete immediately, we want it to come back. We don't want it to wait for forever. Well, we don't want to write something to the USB and have it sit there and wait forever because we unplugged the device. That's just kind of silly. We're starting to set up our ePOL infrastructure. We're calling ePOL on Linux, which is kind of annoying. This is the main mechanism building block on Linux that allows you to actually say, I'm waiting on a file descriptor, and when something comes in on that file descriptor, please wake me up, otherwise I'm going to stay asleep. Yet more boilerplate. We're actually saying what events we want to watch. We want to watch a poll in and a poll out. Poll in is actually a read event. Poll out is a write event. In this particular instance, read events aren't what we're actually working against. We're only doing write events because we're a mouse. We just send stuff. If you're actually doing more advanced HID mechanisms and more advanced HID drivers, like the Echo driver that I have, ePOL in now matters. In this instance, we're adding it and telling Linux, hey, we really want you to pay attention to that file descriptor. Get ready for it with ePOL. We're actually keeping track of time in this particular instance because we want to bounce our cursor back and forth depending upon which second, whether we're on an even or an odd second, whether we want it to go up and to the left or down and to the right. In this particular instance, we've got an ePOL. We'll empty it out. And then the first thing we do is we actually ask ePOL wait and say, hey, can you give us an event? We're going to hang out for however many timeout millis is, which is 1,000 milliseconds, so 1 second. And we want you to get one event. If we don't get any events and it actually returns, we actually wound up with a timeout in this particular instance. And if we wound up with a timeout, then we can write through it. And that mechanism says, okay, we want to write a report. In this instance, the report, again, as I said, is 3 bytes. That's our buttons. We don't have any buttons to push. This is -16. This is -16x and -16y. Or depending upon if it's an even, it's no buttons to push. +16x, +16y. So we bounce back and forth. We write the report. If the report goes through, it should always go through. If we actually are capable of writing the report, we should always write 3 bytes of the report itself. If that fails, something went very wrong. We're going to just die. In this instance, the other thing that can happen is we can get an error. In this instance, woodblock becomes the error because we're unplugged. So when we try and write something to it, it just goes into the ether. In this instance, we want to we're re-enabling a write event. Sorry about the pop-ups. RISP Analyzer can be a little annoying about that. We're re-enabling the write system as we need that event. We'll talk about why we need to re-enable it in a little bit. And then we actually tell the Linux system that we've re-enabled it, and please look for read and write in this particular instance. If we get an unknown error, we just kick it upstairs. If we can't write at all, we're unplugged. All we can do is hang out. If we do get an epoll event, what's going on? We first check to see that the file descriptor is the same as we gave it, which means that we didn't get some weird screwball thing due to epoll, which we won't discuss. Can happen, but as long as you're single-threaded, this shouldn't happen, and this is all single-threaded. Then we're actually looking for whether or not this was a write event, in which point we found a write event. That means somebody plugged us back in. We can actually start writing again, and then we disable the write events coming back from epoll. The reason for that is we will keep getting spammed with write events as long as we can actually write to that file descriptor. And that file descriptor is pretty much empty all the time. In this instance, we can actually hit the epoll. We can return the event struct. If we get a read, somebody attempted to read from us, and that just doesn't work very well. So in that instance, that covers all the bus code that we're doing. So now if I go back into the Ubuntu, you can actually see that when I actually connect and run via that, my cursor starts jumping back and forth. So we've actually managed to create a fake mouse using a BeagleBone, using Rust, and using the Linux USB subsystem. We did it in about 25 minutes. So what I want to say is thanks a lot for attending. I know that was sort of a whirlwind scene of how to do USB HID devices. I'll probably make a talk later at some point where I actually make this work for a much larger HID device, where I talk about how to do this with a debug probe. Anyway, thanks y'all for attending, and I much appreciate your attention. Good luck and enjoy the rest of Oxidize 2020. Have a good one.